In Chapter 11, we're looking at liquids and intermolecular forces. This video considers what's happening at the particle level when we compare gases, liquids, and solids, and introduces the topic of intermolecular forces. Intermolecular, the molecular part. When we've looked at covalent and covalent bonds, these are describing what's taking place within the molecules. The bonding models describe how opposite charges within the molecule are leading to attractions and the bond formation. Whether we're thinking about valence bond theory, molecular orbital theory, it's all about how we can have opposite charges that lead to a net attraction. What leads to attractions between the molecules themselves? Once again, we must have opposite charges attracting each other, and that's what the intermolecular forces are describing. Share with me, what is your prior knowledge of this topic? Have you heard about intermolecular forces before? What do you remember? What do you know? When we looked at ionic compounds, we definitely saw how opposite charges were being attracted to each other. The Born-Haber cycle was describing the formation of getting cations and anions together, and we saw as a collective, the formation of the lattice was leading to the ionic compound. What about a molecular one? So here I show a description for CO2 solid. Carbon dioxide solid is called dry ice. Notice within the molecular compound, I have a discrete molecule, a distinct CO2 molecule. CO2 solid, dry ice, can go directly to CO2 gas. This phase change of going directly from a solid to a gas is called sublimation. I like to think about that because it really shows me and really illustrates how for a molecular substance, we're preserving the molecule, whether it's in a solid, a liquid, or as a gas. Solid, liquid, gas, those are all phases that we're familiar with. Here we see descriptions of chlorine, bromine, and iodine. And notice how the phases are different. Let's connect this to your prior knowledge. Are these skills you have? Can you draw a Lewis structure for CO2? Would you be able to describe the bonding with valence bond theory? Would you be able to describe whether it's polar covalent or simply covalent? I'm not asking necessarily for you to demonstrate those skills, but are those skills that you have? An additional skill, is the molecule polar or nonpolar? The molecule itself. That's an important question when analyzing intermolecular forces. And we learned about that when we saw how we could use Vesper theory to predict the geometry and then consider whether the molecule is polar or not. That's going to be an important skill for us. CO2 is a diatomic molecule, as is Br2 and I2. Notice how they're showing different descriptions as the gas, as the liquid, as the solid. Let me show you a demonstration on this. As you watch the demonstration, try to visualize and think about what's happening at the particle level and ask questions as needed. So let me now consider what I think is taking place at the particle level. So we have descriptions here for something as a gas, as a liquid, and as a crystalline solid. Let's add to that this idea that there are differences in the intermolecular attractions. They're increasing as I go from chlorine to bromine to iodine. They're increasing if we look at those molecules on the periodic table as I'm going down that particular column. The strength of the intermolecular forces are determining whether that substance is a solid, a liquid, or a gas. And by that substance, I mean these diatomic molecules. They're all very similar. They're all nonpolar molecules. But in terms of size, sure looks like we have a pattern that we're going to need to understand. At the particle level, I think those gas molecules are far apart and they have complete freedom of motion. The liquid, they're more packed together. There's random orientations. They can still jostle around. The solid, they're packed together the most tightly. There's this ordered repeating pattern. They can move somewhat, but certainly not as much as the liquid, and definitely not as much as the gas. The kinetic energy, the Ke of the particles, is what the temperature is measuring. At room temperature, CO2, Br2, and I2 all have the same kinetic energy because they are all at room temperature. But the strength of the intermolecular attractions is different. For the gas, the kinetic energy is much greater than any intermolecular attractions that were taking place for the CO2. The kinetic energy is about the same magnitude as the attractions when something is a liquid. And when something is a solid, that amount of kinetic energy is much less than the attractions. These descriptions here of what's taking place at the particle level, those give rise to the different properties, whether something is a gas, a liquid, or a solid. When we're thinking about properties, CO2, I list there its melting point and its boiling point. Between those, it exists as a liquid. We see the range for Br2 and for I2. It's clear that stronger intermolecular forces are affecting the properties. Stronger intermolecular forces are leading to higher boiling points and also higher melting points. In this chapter, we want to connect the intermolecular forces and the various properties and see how they are related. So with this Br2, when it was added in the demonstration to liquid nitrogen, we saw that we had a phase change. Liquid nitrogen is at 77 Kelvin. What changed during this demonstration? Was it the kinetic energy of the Br2 or the intermolecular forces? Share your answer. So in this video, we've looked briefly and compared gases, liquids, and solids, and I mentioned the idea of intermolecular forces. In class, we're going to move on and look specifically at what the intermolecular forces are, what gives rise to them, and how they affect properties.